Halo, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon.
Good afternoon, Doctor.
Good afternoon. I hope everybody are doing well, okay, healthy. And for today, we will continue and we will finish up the chapter regarding the level flight, pull-up maneuvers, as well as the VN diagram. Okay, so we will complete that, and then after I have complete my lecture, I would like Adam Lokman and Adam Yusuf to share the answer for question that not yet being solved since last week. I hope those two can share the answer right after my lecture. My lecture probably around 40 minutes or 1 hour. Okay, after they share their answer, okay, I will play a video, about 50 minutes video from Professor Filipponi regarding aircraft noise. Okay, so besides aircraft performance related with the aerodynamics, there are also other elements that need to be addressed, such as the aircraft noise. So how the measurement was done, and what are the things that you need to know regarding the ICAO. Yeah, thank you, Izul Aiman. I think I'm not saying 100%, but at least 98%. I think recovering from the back pain. Okay, don't forget to put your metric number in the chat box. That's another thing. Okay, regarding aircraft noise, there are regulations set by the international authority. Okay, so it is one of the things that is become a challenge. Okay, especially to those airports where nearby the nearby city center or nearby residents. Okay, so people are not happy with the noise generated or left behind the vortices, right? Even the trail of the aircraft, that's become a big issue, especially in the UK. I still remember, because people are complaining because in the UK, it is not easy to see a blue sky. Okay, it is not easy. Most of the day throughout the year, it is cloudy. Okay, like what we have in the past few days in Malaysia. So that is what they are having throughout the year. So blue skies is very important for them. So if there is a trail from the aircraft, aircraft trail, right, the white color, so that's become a eyesore, menyakitkan mata lah, to the people, so to the public. So that's also something that they are looking at right now, beside aircraft noise. But yeah, there are a lot of things that's happening, right? Okay, without further ado, I think we will proceed with my lecture. Okay, just to recap what we have before. Okay, what we have last week. Let's go back to the first slide. Okay, what we have last meeting last week. We cover the level turn flight, pull up. I think pull up and pull down maneuvers is not yet we only cover level turn flight. And for today, we will cover the other two parts, pull up and pull down maneuvers, as well as the VN diagram. Okay. For the VN diagram, it is very, very important for you. Not only to the engineers, but as well as to the pilots, okay, who are planning to get a pilot license later on. If I'm not mistaken, two of your seniors, the alumni from this program, they become a pilot. At least two that I know. One is Chinese, one is Malay, if I'm not mistaken. Also my senior. Okay, they took the pilot license. I'm not sure. They end up as a pilot or they end up as engineer. Okay, I lost contact with them. Okay, so last week we look into this part, right? Level turn flight. So what is level turn flight? Where the aircraft is turning without losing its altitude, meaning that the aircraft is turning and also maintaining its height, its altitude. Okay, so that is what we call level turn flight. And there are on how to determine the radius of the turn radius, the rate at which the turning is progress, right? And the maximum load factor and also the minimum speed at that particular point. So this is a VSTOL lah. Okay, now we want to look into what we call pull up and pull down maneuvers. Okay, so consider an airplane initially in straight and level flight where L equal to W. The pilot suddenly pitch up the airplane to a higher angle of attack such that the lift suddenly increases. Okay, meaning that the lift is now more than the weight lah. Okay, because lift is more than the weight, the aircraft will arch upwards. It's going up. Okay, in a some sort of circular motion lah. Okay, as what we can see in figure 6.5 here. The flight path become curved in the vertical plane. Okay, so the altitude is increasing lah in this case because it's pulling up, right? The altitude is increasing. The height of the aircraft with respect to the ground is increasing with a turn radius of R. Okay, this one R, turn rate of d theta dt, or this is also omega lah in this case. This is called pull up maneuvers. Okay, like what we have here. So from the Newton second law, I would say this is from the Newton second law anyway, but okay, but this is being expanded lah. So this is initially it is mf equal to ma, right? So this is a. If you solve this, the unit is acceleration. Okay, so m, the mass, times the acceleration of the aircraft while pulling up. Okay, but in this case it is in the form of v and r because we want to see the relation between the speed as well as the radius of the turn. Okay, and that is equal to lift, okay, minus the w cosine of theta. This is theta, u here is theta. Okay, this u is theta. So L is this one, w cosine theta is the component which is in the direction of L. Okay, if you look here, w, so w, if you expand it, if you look into the component in the X and Y direction, so you will see there is a the cosine component of W that is parallel to the direction of L, in the opposite direction, of course, right? It's going down. Okay, and so this is what we have. Okay, but if there is no pulling up, okay, or we can say the aircraft is suddenly, so this down here, moreover, okay, the instantaneous pull up is of much greater interest, and we will focus on it. Moreover, we assume the instantaneous suddenly pull up is initiated from straight and level horizontal flight. The corresponding theta is equal to 0. And this is what you have lah. This is just right before the aircraft start to pull up. Okay, just a very last moment lah before the aircraft start to pull up. Okay, as in the case of level turn, the pull up performance characteristic of greatest interest are the turn radius r and the turn rate omega, which is the rate change of the angle theta. Okay, u here is nothing but theta. This one is theta. The instantaneous turn radius is obtained from this equation. Okay, actually you have see this similar kind of this before, and this one is nothing but it is derived from this part here. Oh, sorry, yeah, from this one. Okay, you move R to the right hand side, and L minus W, you put it down, so you will end up like this, and you simplify from here. You can M is actually W over G, right? Okay, M is W over G, and you have and down here you divide this by W, so you have L over W, and W over W become 1. Okay, because you divide the denominator and numerator by W, so this is cancelled up. Okay, so now you have L over W. Okay, L over W, as what we have seen before, that is your load factor. Okay, N. So L over W here, you replace by N, and that's it. This is what you get. Okay, L over W divide by, you replace it by N, the load factor. So you have this equation. Then if you want to see the turn rate or omega, as you know, omega is, V is actually equal to omega R. Okay, V equal to omega R, or omega is equal to V over R. Okay, from here, you can transform it into this. Okay, so this is for the pull up maneuvers. And finally, you will have similarly like this lah. Okay, so this equation is almost similar to this one. Sorry. Okay, this one is pull up. For pull down, this one is going down, right? The pull down maneuvers. The only changes is N, this sign. Okay, previously you see this is minus, right? N minus 1. But for pull down, if you work on it, because L and W is in the same direction, you see, L and W is in the same direction, right? So from here, you rederive and you will end up, the sign here become a positive, unlike the pull up maneuvers, which is negative. Okay. Any questions so far? Okay. So if
Yeah,
you
doctor.
no, okay, no question. Okay. As we can see before, when we talk about a level turn flight, this one 6.9, where was it? 6.9. Yeah, this one. This is for level turn flight. You have this question, right? If you look here, n is to the power of 2, and you have a square root here. Okay, this is when you do the derivation lah. Right. But for this one, where is it? Okay, unlike the pull up and pull down maneuvers, you didn't have a square root and the power of 2. That is the differences lah between this and this one. And from the pull up compared to pull down, you just change the minus into plus sign. Okay. Then in the limit of large load factor is very big, these three equations reduce to the same form. Okay. If n is very large, okay, it become very dominant, I would say. Probably the value is 8 or 9. So it doesn't matter, you minus with 1 or plus 1. The range will not change that much. Sorry, the radius will not change that much. So you can basically simplify into this equation. Okay. Similarly, consider the expression for turn rate for level turn, pull up, and pull down maneuvers as repeated here. Okay. This is for omega. Then, okay, level turn, pull up, pull down. Okay. And all this, in the case of large load factor like this one, it will reduce to this one, Gn over V free stream. Okay, that is the actually that is the pull up and pull down maneuvers lah. Okay, so now we want to move into the next part. Where was it? Okay, the pull up and pull down maneuvers considered here are treated as instantaneous, and in contrast to the sustained maneuver, sustained turn, discussed in section 6.2. For instantaneous maneuvers, the thrust limitation discussed are not relevant. Why? And instantaneous maneuvers is initiated by a sudden change of lift. When we are talking about instantaneous maneuvers just now, you basically don't consider this theta, right? Because theta is equal to 0. Instantaneous pull up in this case. So that is what it means. Then, okay. Now we want to move into what we call VN diagram. Okay, this is nothing but on how to determine the minimum radius and also the maximum turn rate for that particular aircraft at that particular condition. Okay, when we are talking the VN diagram, there are two things that I would like to highlight. One is the limitation of the pilot himself or herself lah. Okay, because because we are human, we have a blood vessel in our body, and when your body experiencing a large G force, N is also G force, load factor, same thing lah. We're experiencing, let's say, G force of 6, for example, or 9, then due to the inertia of the blood inside your vein, that will actually develop or make you fainted lah, dizzy. Okay, at first probably dizzy, then finally you will lost control, okay, of your body and also the plane. So that is one thing that you must remember when you are designing an aircraft, that you cannot simply design it to perform. Let's say you want your aircraft to perform 20, n equal to 20. Okay, the load factor is 20. That is what we call over design, because you don't need to design something that is way too much. Okay, that is a waste of money, waste of time, waste of effort. Okay, that is not practical, because human cannot sustain more than 9 g-force. Load factor of 9 or 9g lah. So basically what you need to consider as well is the structure of the aircraft itself, because for the aircraft there are rivets, there are screws, there are bolts, there are nuts, there are a lot of joining parts, right? So there are also weaker part on that particular component that will break due to the large g-force or loads. So there are a lot of other structural limitation when you are talking about the load factor or the g-force that the aircraft should sustain lah. Okay, so if you want to design an aircraft typically for small two-seater aircraft, the positive load factor is around 4-5. Okay, 4 to 5. I think around just below 5 lah. That is the maximum for the positive load factor, and the negative load factor, if let's say the aircraft is performing upside down flight, right? When the aircraft is performing upside down flight, then the g-force is negative, because the direction of the lift is pointing down. Okay, then the aircraft is the lift is still pointing up, but the orientation of the aircraft is upside down. That's why it is a negative load factor lah. So the negative load factor when the aircraft is performing upside down motion, for example, then the aircraft the load factor is around -2. Okay, around that value lah. So we will see example after this. So there are there are structural limitations on the maximum load factor allowed for a given airplane. These structural limitations were not considered in the previous section, so we have to examine them now. There are two categories of structural limitation in airplane design. One is the limit load factor. This is the boundary associated with the permanent structural deformation of one or more parts of the airplane. Okay, if the load factor is less than the limit load factor, okay, the structure may deflect during a maneuver. Okay, but it will return to original state when the n is equal to 1. What does it mean by n equal to 1? N equal to 1 means the lift is equal to the weight. Okay, if n is greater than the limit load factor, then the airplane structure will experience a permanent deformation. Okay, that is, it will incur structural damage. So another part is ultimate load factor, this is the boundary associated with the outright structural failure. If the load factor is greater than the ultimate load factor, parts of the aircraft will break. Okay, this is the VN diagram. Okay, this is the VN diagram. On the y-axis here, we have a load factor N, and down here, we are on the x-axis, we have the aircraft velocity lah. Okay, aircraft velocity, and the unit here we use knots, but you can change the units anyway. Okay, what we want to see here is this. If you look carefully, the curve that is going up, okay, that is the positive load factor, because n, the value of n is positive going up, and you also see that there are also negative load factor. This is typically when the aircraft is performing upside down flat, okay, like the aerobatic aircraft. Okay, so typically the aircraft will also need to have this capability or capacity to perform to have a negative load factor. Okay, why this area here is called stall area? Let me, okay, I can go something there. Okay, the area here, this is the stall area. Similarly, here, this is your stall area. Okay, this is your stall area lah. And why this line is curving up? Okay, as you know, N is equal to lift over weight. And lift is actually half rho V square S C L. And W is W lah. And as you can see, V is square. Okay, V is square. So when you have this square, and therefore you have a curving up lah. It is not linear, right? So this is the why it is curving up. Okay, probably later on you want to know why, and also why it is curving down. This is same thing lah. Okay, why it is going down, because as I said, the aircraft is performing upside down, so the direction of the lift is negative, because with respect to the orientation of the aircraft at that particular moment, the lift is pointing in the reverse direction with respect to the aircraft. With respect to the aircraft, okay, let's say the aircraft is flying normal. Okay, the lift is pointing upwards, right? Lift is pointing upwards. So when the aircraft is flying upside down, okay, this is a tail. Flying upside down, the lift is still there, but with respect to the orientation of the aircraft, okay, if you compare these two, you see that is why it is a negative. Okay, I hope you understand. And therefore, when it is negative, this one is negative, and when you insert all the values, then it become a negative value. It's going down, curving like that. I hope you understand. Okay, that's one thing. Then how we want to know the value of this curve? Okay, so this particular lines is generated by inserting. If let's say we stick V, or we say that V is ranging from 0 to, I don't know here, around 580, for example. V is, let's say, from 0 to 300, for example, or something like that. Okay, or you can go up until here, no, never mind. Okay, what we interested is, let's say, from 0 to 300, for example, V. That is the value of V. And rho is constant. Let's say the aircraft is flying at the same altitude. So we assume that the rho is constant. S is the wing area. You cannot change the wing area during flight. Okay, you cannot simply go to the wing and put something to extend the size of the wing. That cannot be done unless if you are talking about if you have a flap or slat on the aircraft which can be deployed, that is another story. Okay. And then in this case, if you want to determine this position point here or down here, that is, if you can put CL, let's say the value, let's say 1.2, so you put it there, then you vary the V from 0 to, let's say, 300 knots. In this case, it is a knot. So you will get this curve. Okay. One of the assignment later on, I will ask you to create the VN diagram with a certain parameter that I will supply. So you need to create the VN diagram. I want to know exactly, do you know or not on how to create this VN diagram? Okay, from this particular VN diagram, as you can see, of course, the description is here, but I don't want to read this. Okay, you can read it on your own later on. For me, I can explain it without actually look at this. Okay, let's say you are flying at a V1. V1 is here, right? And let's say at that particular condition, V1 here, let's say 150 knots. And then let's say CL at this particular condition is 1.2. This is my assumption. It can be something else. Okay, it can be something else. Okay, if you want to know what is the value of CL, let me see. Let's new share. If you still remember, CL alpha, see, this is your maximum, right? Let's say the maximum is 1.2, for example. This is what I'm talking about. Okay, if this value is 1.8 or 2.0, I don't know. It depends. Okay, I'm just guessing a number. Okay, for now. Okay, I hope you get my point there. Okay, so let's say you fix at 150 knots. And then you put the CL value of let's say 1. Oh yeah. Okay, no need to read this one because I just see this value. It is by coincidence is the same value as what I'm saying just now, 1.2. But anyway, there is something else. Okay, so in this case, one of the another things that you need to know, which is missing from this particular figure, is the minimum speed the aircraft should fly, the stall speed. They should have another line here. Okay, if you refer to, oops. Okay, if you refer to the earlier, Okay, you see this one? Normal stall speed, this line here. Okay. Of course, this one is a mph, miles per hour, but just want to show you that the aircraft should, basically the aircraft, this figure is much better lah. The aircraft should fly within this green shaded area. Okay, green shaded area. If the aircraft is flying less than this one, is, let's say, this one, I think 65, I don't know, 64. 1, 2, 3, 4, 5, 5. Yeah, this one is 64, I think. Okay, let's say the aircraft is flying less than 64 miles per hour, then the aircraft will stall. Okay, so that's why it starts from here, because if you want to fly an aircraft, there are a minimum speed that you should fly. Okay, otherwise the airflow is on the wing is not stable, and yeah, you will stall basically, not enough lift to sustain the flight. Okay, and if you are flying above this red line, what happens is that you will also stall. Okay, this one, if you flying above this line, if you are flying let's say here or here or here or down here, your aircraft will stall. Okay, then if you go further, okay, you increase your speed of your aircraft. Okay, you basically apa ni, tekan habis lah throttle. Okay, so if you push the aircraft further with the available thrust that you have from the engine or from the propeller, so you can only fly at this speed, about 180 miles per hour. Why? If you go faster than that, okay, what happens is the structure of your aircraft will not sustain that that speed. Okay, you have this is what we call maximum structural cruise speed. Okay, then if let's say you are flying at 160 knot here, okay, 160 knot and 60 knot, and then you are actually pulling up. Let's say you want to pull up at this particular moment. Okay, you want to pull up your aircraft because in front of you there is a large mountain or there is a large building that you want to avoid. Then you must consider this structural damage. Okay, if you want to perform that sort of maneuvers. Okay, so that's why we have this VN diagram to make sure that the flight is safe. Okay, the pilot is safe, the structure of the aircraft is also safe, in the sense that nothing is damaged lah. The component of each component of the aircraft is within the safe limits of operation. Okay, you see this amber color, right? And then further that you have a red color, red region here. This is the structural failure. The wing might fall off, the wing might break. Okay, the rivet might come out. So there are this is the ultimate lah. If you fly in this red region, that's it lah. Okay, you need to have a parachute lah. Anyway, right? Otherwise, you are in trouble, in big trouble. Okay. Okay, that is the things for BN diagram. Oops. Okay. So that is the BN diagram. Oops. Yeah, this one. I have a video here. What was it? Okay, let's share sound. Okay. Okay, I think now you can hear the sound.
In straight and level flight, lift equals weight and the load factor is said to be 1. In a bank turn, the vertical lift component that opposes weight is reduced. To maintain the turn without losing any altitude, the pilot must increase the angle of attack to generate more lift. This increases the loading on the wings and increases the aeroplane's apparent weight.
So in this particular moment, as I explained earlier, this is where your load factor acting on the aircraft is higher than 1. Okay.
So if you could put a scale under the aeroplane, it would show more weight. This is due to the centrifugal force acting on the aeroplane outwards from the centre of the turn. No matter how fast or how big the aeroplane is, in a level and balanced turn, the load factor will be higher. How much higher? We can work it out using this formula. So at 45 degrees angle of bank, for example, the load factor is 1.4. The greater the angle of bank, the higher the load factor, and this increase is exponential. It's important to understand that stall speed also increases with the load factor. How much more? We can work it out using this formula. For example, if the aeroplane stall speed is 50 knots, in a 45-degree turn, where the load factor is 1.4, the stall speed becomes 64 knots. What do you think happens at 90-degree angle of bank turn? Please comment below.
Okay, that is a bit of the explanation about how you must know on how the load factor is changing during this turning, whether it is a level turn, pull up or pull down. The same concept is applied. The same concept is applied. So it is nothing but just what called this is a corner velocity. Another thing that I forgot to highlight is this point B here. This point B is actually the what you call it the maneuvering flight. Okay, I need to get the right names. I think on the previous one is there. Yeah, maneuvering speed. Okay, this is point B actually. Maneuvering speed. This maximum point here. Okay. Okay, that is the maneuvering speed or maneuvering point lah, point B, this one. Okay, this is another example. I think you can go through. Yeah, this one, CLmax 1.2. Just like what I have assumed. Okay, so for this is a typical positive load factor and negative load factor for different type of aircraft. If you see normal general aviation, the load factor, the positive load factor is around up to 4 okay, 3.8 or 4, something like that. And the negative load factor is about 1.5 at the maximum. The aerobatic general aviation 6, and negative is -3. Okay, 6, -3. This one. If you look this graph here, this line from B to C. Okay. For aerobatic aircraft, this BC should be aligned with this one, 6. Okay, it should be from here. Oops, sorry. There, 6 lah. Okay, should be there. So, okay. Then for civil transport aircraft, about 4, and the negative is about -2. But for fighter aircraft, of course, the fighter aircraft need to perform combat maneuvers, right, to avoid being shut down. So by the enemy aircraft. So the load factor is very high. The positive is up to 9, and the negative load factor is -6, or could even more for the modern generation of fighter aircraft. I'm not sure, because sometimes they will not publish this data, okay, to us. Okay, that's it for this lecture. I will proceed with the lecture by Prof. Filipponi. But before that, I would like Adam Lokman and Adam Yusof to share your answer. Don't forget to put your metric number on the chat box. Adam Lokman and Adam Yusof. Muhammad Adam Lokman, are you with us? Can you just share your screen for the solution for that particular problem? I have the solution with me. Where is it? I need to find it out. Oh. Yeah, Muhammad Adam Lokman. Or you are not ready? Okay, you are sharing. Okay. Let's see. I just want to check the method. Okay, you are using the correct CL square root of 3 CD naught over K. I think that's correct. 3 CD naught over K. Yeah, that's correct. And then you are using CL. You can share your voice if you want to explain it, no problem. And then L over D max. And L over D max. 1/4. Yeah, this one is correct. The right hand side is correct. Endurance of propeller. Okay. So what's the final answer? That one. How did you convert the value of C? You cannot just simply put 0.4 like that. You need to convert it. Okay, you need to convert into second. You need to convert 0.4 for the specific fuel consumption. I think, or you have a mic problem. But anyway, I think the first two parts up here, you are using this when you calculate 1.1019. That I think that's correct. And then you calculate the L over D max. That is also, the approach is correct. Okay. the only comment from me is you need to double check the 0.4 here, down here. You need to convert it. I think that when that is done, you should get a better answer lah. This is not correct lah. 0.028 hours. I think that is something need to be done. Okay, thank you. Okay, okay, thank you. How about the other Adam?
Doctor, for our team, we got about 8 hours for the first part and 6 hours for the second part of the answer, Doctor.
Can you share it here? Do you have it?
Sure, Doctor.
Okay. Okay.
Doctor, this is the change value.
Yeah, yeah.
So I'll just skip. Here is the conversion for the specific fuel consumption, Doctor. So we are a bit weak in the metric system, so we converted it to the standard units first, and then finished the conversion, and then came back to the metric unit again. So, Doctor, for 1 pound per horsepower hour, we can convert it to kilogram per kilowatt hour.
Okay.
If we just multiply by this number, and then from kilowatt hour, we can convert that to Newton meter per second by multiplying, by dividing with 1000. And then after that, from kilogram per Newton hour, we can just multiply it by this value to get it back into the metric systems unit, the pound per pound force hour. Okay. So that is what we did in this calculation, Doctor. From 0.4, we just followed this whole procedure, and then we got 2.386 into 10 to the power minus 3 pound per pound force hour. Okay. And when we just applied that to the equation, Doctor, for the first part, we got 8.2357 hours, and for the second one, we got a 6.6007 hours.
Okay, I think that's that is makes sense lah. Okay, that is makes sense. Okay, I think what you have done here, CL over CD. Can you go to the previous part?
Yes, Doctor.
How do you calculate CL? Sorry, how do you calculate CL?
Oh, this is by following the equation that Doctor provided us, and not the previous one.
Okay.
So you 1 by 4 into 3 by.
That's correct. Then how about you calculate for the other part? CL to the power of 3 by 2 over CD? Did you use the same?
For this one, we used this equation, Doctor.
No.
D by 4, CD naught, K whole root.
No. You need to use the CL to the power of 3 by 2 over CD.
Doctor, actually for this equation, they only provide the main equation says CD by CL by CD. So that is why we went with this equation.
This
Doctor.
one, I don't think this one is for propeller aircraft. Can you double check? Because for propeller aircraft, the equation for endurance is different.
Okay, Doctor. Then I'll double check, Doctor.
Yeah.
But this one is correct, right, Doctor? This one is for propeller.
Yeah. Can I share mine?
Sure.
Okay. You need to use this one, this equation for the endurance. This one. Okay, Shan, I hope you can see this. You need to use this equation to calculate for
the second part too, because for the second part, Doctor, it says constant AOA and constant airspeed. one is Dr. airspeed and one is constant altitude. So I thought that there will be two different equations to solve.
I think you should maintain with this one. I will
Okay.
double check on that. But I think you have to use the same equation. Okay, anyway, so okay, that's very good. So we finally arrived to the almost the right answer. Okay, even though just I think one minor update on that part. So congratulations, you have finally managed to solve the problems. Sometimes that's why to understand the derivation is very important. Otherwise, you are in the dark. Okay, you don't know which equation you should use to determine the CL, for example, and which equation that you need to use when you want to determine the other parameter in that particular formulation or problem. Okay, without further ado, I will share with you the recorded videos by Prof. Filipponi. He actually supposed to share his presentation during the AROS conference on the 12th of December. However, due to the there was my mistake as well, due to our lack of communication, the time, because it is like this. If you are compare or you check the time difference between here in Malaysia and the UK, sometimes in the year it is 7 hours, and sometimes during the year it is 8 hours. Okay, that is what we call a day saving light lah. Especially during winter time, you have the time difference is 8 hours, not 7 hours. Okay, so due to that, we have a problem. Okay, so actually he's supposed to be with me during the presentation at 7 in the morning. Instead, he thought he's supposed to be with me during the conference at 9 a.m. in the morning in the UK, UK time. So yeah, that is the problem lah, that what we have. But anyway, this is what I want to share with you. This one. Okay, I think this one. This is about 50 minutes. Okay, I hope you can hear this. Okay, let me double check that. Okay, share sound.
Hello, this is Antonio Filipponi from the University of Manchester, and I'm recording my presentation to the AROS conference. I regret that I'm unable to join you at this conference because of the travel restrictions we have around the world at the moment. Today, I'm going to talk about aviation and environment.
Before I proceed, I think I should tell you who is he actually. Okay, he is actually the author of this particular book. Okay, Flight Performance of Fixed and Rotary Wing Aircraft. Okay, Professor Antonio Filipponi. This is a book by him lah. Okay, on aircraft performance. In this particular book, there are two parts. One is about fixed wing aircraft, and the other part is about the rotary wing aircraft, like rotary wing aircraft, which is like helicopter, or you can relate it to drone as well. Okay. Okay, let's continue back on that part. Sorry, interrupt you on that part. Okay.
Particularly on aircraft noise, is an area on which we're doing a lot of research.
Can you hear the sound?
Yes, doctor.
Okay, thank you.
So to give you an introduction, I'm gonna talk to you about an historical perspective of aviation. 100 years ago, what you needed was capability. So you needed to show that your airplane could fly faster, could fly longer, it could carry more payloads. Later on, say after the Second World War, the focus was on commerciality. That means, trying to make money from your aircraft operations. And so there was an expansion of both passenger traffic and freight traffic, which peaked in 2019. The current focus is on sustainability because aviation has expanded so much and emissions are so high profile that the concept of sustainability is in fact a question of the survival of the entire industry. Among sustainability, there is obviously noise, on which I'm going to talk about today, as well as engine exhaust emissions and effects on climate change, which would be the subject of a different talk. And finally, we are in a world where everything is interconnected. So we have new issues of security. So we call it also cybersecurity. There is the opportunity of looking at issues of, for example, air navigation and other aspects of a flight, from situations on the ground to situations on the air. And therefore, the entire issue of sustainability and security is what the focus of aviation will be in the next decades, in my opinion. So just to indicate what my talk is going about is, again, within the area of sustainability is on aircraft noise. The presentation will have essentially two parts. Part one is looking at the noise context and the noise measurements at the airfield. And part two will be on trajectory management and trajectory optimization. Since my talk is obviously restricted in time, I cannot talk about the simulation methods, which will be a different subject. I will draw some conclusion and a summary out of these two parts later on. So let's look first of all at the noise context. In a recent academic paper I read, it appears that if we had no ears, then the subject wouldn't be that important. The issue we have is that people respond differently. So there is a behavioral sort of response and also physiological response. So in terms of behavioral response, there are, of course, disturbances. There are, effects of annoyance. The whole concept of annoyance is central to the issue of aircraft noise. And from a noise, you have people actually complaining. And there are various ways of complaining. Physiological are some aspects which have been actually considered by people working in public health. So that is not my subject at all, but just I want to mention that there is biological response like hypertension, loss of hearing, a number of other aspects of which there is a lot of technical literature out there. In terms of behavioral, I mean, this is quite interesting because it's not just a question of measuring noise, on which I'm going to talk about in a few minutes, is how noise is basically felt by people on the ground. There was a talk I had recently with recently it was before the pandemic, with people, experts on noise at the Heathrow Airport in London. And the one complaint was that the Airbus A380 is more noisy than a Boeing 747, although the opposite is true. Apparently, the reason is that the takeoff trajectory of an Airbus A380 is more shallow in order to reduce noise. So people on the ground see this airplane much bigger, much closer, and they are to believe that the noise is actually higher because you got this big beast up in the sky, you know, very close to you. So the opposite is true. So it's a question of a psychology in there. So the ability of looking at the big things that are threatening from the sky, so they sound more noisy. So this is not obviously true. There are other things happening there. And so the issue of psychology, the behavior is very important, is central to the whole aspect of noise. So we started in 1970s, and there was the first sort of attempt to certify aircraft noise. And that was due to complaints on the ground due to the presence of supersonic aircraft, which was called the Concorde. Now that airplane is not flying anymore. But we know that people were sort of, you know, complaining in New York. This is an anecdote told us by this Mr. Smith in 1989, who was involved with the first generation of aircraft certification procedures. And the people were complaining about noise, and they didn't even hear that the aircraft had landed. So you see, it's very, very self-centered, and you need to take into account that, you know, we ourselves as humans, we also create a lot of noise. Obviously, there are nowadays airport noise restrictions, regulations all around the world. There are about 600, maybe 650 airports around the world that have some form of noise restriction. So there are certification requirements, for example, the ICAO, various other international organizations like the European Safety Aviation, the EASA, based in Germany. And this essentially in all flight performance, design, and operation. Now, the ICAO these days recognize that you know, you cannot just do one thing to reduce noise, and they take a so-called balanced approach. This means that you do a noise reduction at the source. So look at the noise sources, something I'm not able to talk about today because it takes too long. There would be improvements in the use of land around the airports, optimal flight procedures, which I'm going to discuss very shortly, and finally would be the restriction of operation. These are called quotas. So there is a concept to assign a quota to each aircraft, depending on the category. And each airport is assigned a quota, and they cannot exceed that quota during the 24-hour period. That means if you have, for example, 100 airplanes of a mixed fleet taking off and landing over a period of 24 hours, you cannot add another airplane unless you're able to demonstrate that the noise is reduced somewhere else in the whole operations of that particular airport. So the noise regulations essentially are two types. One is a certification, which is essentially coming with a certificate that you need to hold. So it's a noise type certificate, and then will be the operational, is what the aircraft is doing every day in and out of any airport around the world. So certification started with the Chapter 2, as they're called. Chapter 2 were the initial rules in the 1970s. They were improved. Improved means that the noise level allowed actually decreased at a number of operating points. These are takeoff or flyover, landing, and the sideline. So they this Chapter 3 rules, they basically make the current baseline in numerical values, but they've been further improved at the beginning of the century. So in 2001, there was a Chapter 4, which was essentially agreed at the ICAO level, which means there are the same rules as Chapter 3 minus 10 dB margin. So 10 dB margin is calculated at 3 operating points. One is flyover, one is sideline, another one is landing. In 2013, just some years ago, there was a further improvement of further restrictions on these regulations. This is called the Chapter 14, which means that you get to take the current baseline of Chapter 3 and decrease 17 dB over 3 operating point. So you can see that from Chapter 4 to Chapter 14, there is an overall decrease in noise by 7 dB. And there is a new special rule for all airplanes that have a gross weight less than 55 metric tons. These rules became effective in 2017 for the larger airplanes, and just 1 year ago for all airplanes. So that would include airplanes at weights less than 55 metric tons. So if you have an airplane which is been certified under Chapter 2, those airplanes will not be allowed to fly anymore. So we're talking about the first generation of jet airplanes, of which there are very, very few flying around the world. So that Chapter 2 is now being phased out. Now, how do you actually measure noise? As I said, that this is all psychological. You can't just make up a number. Certainly measuring noise with the sound level meter, as I'm going to explain in a moment, is just not enough. So when you look at this chart, what you see is that there is a noise level. Essentially, there is this line here. So you are, say, at the point where you're trying to measure noise. So LP is noise measured in the sound pressure level. The noise increases. It reaches a local maximum here, then there is an absolute maximum, and then eventually decreases. There may be cases where you have some local increase of noise after a certain time. At this point where you have the maximum here, essentially the airplane is overhead if it's flying at a low speed and the low altitude. It will not be exactly overhead to Mach number effects if it is flying at cruise altitude. Here the point is that now you have a signal that you have measured, okay, and out of the signal you need to be able to draw some sort of a metric, which we call an integral metric. So what we do, essentially, we take the peak, then we take a 10 dB down. So you go down 10 dB from the peak, and that would be shown by this arrow here. And then you calculate the time, and the time is this one here. Now, in this particular instance, there is also a small amount of time in which the noise is above this 10 dB down. So you got to 2 times, is this one, T10 prime and T second there, and this is the sum of all times when the noise is above that limit. At that point, you need to do a bit more mathematical procedures. You need to do some tonal correction, which is psychological correction, and then you do an integral over this time that is being given here. And you come up with a number. Ultimately, there are about 5 or 6 steps in doing this. A number which is called the EPNL. This is the effective perceived noise level, and that's measured in dB. This is the metric that is used to certify commercial airplanes today. So when you say you got a certification type and you are complying with whatever current regulation you have, in this case it's Chapter 14, you need to demonstrate that your noise level is below what is being prescribed by certain margin according to this measure, which is EPNL. There is a host of other metrics, which of course I can't describe today, but I have a short table here. They're all important in measuring aircraft noise. For example, you got SEL, which is sound exposure level, is used very often, particularly for general aviation airplane. Then you have a DNL, which is day and night average sound level. This is an integral metric, which essentially takes into account the number of operations over either the 24-hour day or over the day, which is essentially given as 7 in the morning to 23 hours. And then would be the night time between 23 hours and 7 next morning. So you can actually measure the effects of night flights or daytime flights, and the number of other measures, which I'm not going to discuss here. So I just mentioned that the PNL, and then it would be the maximum perceived noise level, which is part of the operations which are required to construct the EPNL. There are other things like the TAUD, which is a time audible. That depends on what is the background noise. So if you got a very high background noise, so you are, for example, in the middle of a busy city, then you have background noise of the order of 70 dBs. So any flights around maybe 75 dBs is not really audible. So anything that has a 10 dB difference is not perhaps very, very important. So there are quite a few relevant metrics. These are qualified by the ANSI, so the American standard. And there are at least 16 of this sort of metrics, which are either weighted metrics or tone-corrected noise metrics, integral metrics, and so on. They're all standardized by the ANSI and by other institutions around the world. So there is a very strange thing with acoustics, that the sum is obviously not linear. The sum is logarithmic, and therefore you get some strange results when you're trying to sum the effects of multiple sources. Clearly, on an aircraft, you have sources from various systems. You have, in case of landing, you got a landing gear, you got the flaps, you got the slats, you got the wing, you got the engine, and the engine will have several components and so on. So the way you sum the noise is through this log sum. So basically what you need to do is to go back into decimal scale and then sum, and then come back to the log scale. And this is some very, very bizarre effects. So for example, if you have 3 noise sources, 1, 2, 3, which have 90 dB, the sum is 94.8 dB. So it's not, 270. And the other very bizarre thing is that if you have 3 noise sources of the 0 dB, 0 plus 0 plus 0 is not 0, is 4.3. So this is what happens in the case of log sum. Now, here I need to be careful about what I say, because only sound pressure level can be summed. EP&L values cannot be summed, because EP&L values are already integral metrics. Okay, so this has to be clear. Only sound pressure level can be summed. So log operations are very tricky. They're not very sort of intuition easy to grasp, but these are important concepts in all aircraft noise. And the other important thing is that the doubling of sources basically increases the noise by just 3 dB. So that's one of the bizarre results of log sums. So let's look now at the measurements considerations. Now, the problem with the measurements is that if you want to take measurements of aircraft noise, you have to be outdoor. And that's very different from being in the lab. The lab is an ideal situation, is very controlled, very repeatable. If you're not happy with the results, you can repeat them again. You probably get almost the same numbers. So what you have is a non-acoustic sources. You have repeatable experiments. Everything is nice and clean. When you're measuring aircraft noise, you are inevitably in an open field where it is uncertain, is uncontrollable, is subject to random events. And of course, there will be the weather, depending on where you are. I mean, here in the UK, you've got to consider, the presence of wind, rain very often, heat not very often, but cold, birds, or the noise. For example, external noise sources, you got the ground reflections, you got the stochastic events, you got various sources that will cause some a sort of background contamination of your source. An example is given here. So if you stay at a chosen location and try to measure with your device, we'll find that here you essentially got your time in minutes. So you have your device keeps running. And there is a number of events. You can set what is called the trigger level. So you can tell your measurement device not to trigger recording. So this is digital recording if the noise is below a certain level. In this case, I think I fixed that being at 52 dBs. So anything below 52 dBs is not recorded. So let's say that, 52 dBs you set the trigger, and then you have a sort of very, very sharp noise in here. Then you have another sharp noise maybe half a minute later. Then there is another noise which lasts about a minute, and so on. And so what happens is that each noise source will have its own characteristics in terms of the peak, duration, and the frequency. And some of the modern systems have a built-in sort of, I wouldn't call it artificial intelligence. It's just a clever system to basically screen some of this unwanted noise. So it's very easy to basically discard the community noise, because it will be sort of random event lasting maybe a second or that sort of thing. And what we know is that an aircraft event just lasts about a minute, depending on the situation you are, whether this is takeoff or landing. It lasts about maybe 45 seconds to a minute, and therefore anything lasting less is probably going to be a contamination in your system. Trains, for example, are known for giving a very high and very sharp increase in noise, but only for a very low time. Motorcycles are very, very noisy, but their noise lasts only a few seconds because they just run away very, very quickly. So you can build a system where you automatically filter out noise from a community, noise from ground transportation, and other things that probably are not going to be aircraft noise. Perhaps you need to do a bit of manual work as well, just to make sure that you got really some aircraft noise that you really want to measure. So aircraft noise here says 30 seconds, but reality can be as much as a minute. So airport noise measurements. So what you have is if you're on approach, there are three measuring points, as we call them. One is approach, one is lateral, and one is back of flyover. The approach is essentially is 2,000 meters. The point will be 2,000 meters from the runway threshold. And then the cutback is essentially 6.5 kilometers or 6,500 meters from brake release points. So these are meters, and these are also meters. And the lateral is a point which is basically 450 meters on the side, on the takeoff sort of side of the runway. Now, the thing is, this is required for certification, but the reality is that the communities are all around the airplane, at the airport, sorry, and of course that they would be placed in any location that you would imagine there. So you got this colored areas, which are urban areas, okay, and the people obviously would be living in those areas, and they will hear a noise which is not exactly the same as being certified. Okay, so ideally what you have is a situation where you need to place measurement devices all around the airfield, and we're talking about scales of several kilometers in each direction, and this is totally impractical. Okay, this is totally impractical. Now the fact is many airports around the world tend to do a noise mapping, which means they try to draw some ISO noise contours and just to try to, tell the communities around, this is the noise level you would expect if you live in this area. I'm going to show you shortly the example of one simulation that we do here in our research. So this sort of graph here with the distribution of microphones is not realistic at all, and therefore we need to resort to simulation, and therefore from there we do what's called the noise mapping or noise footprints at the airports. Airport noise measurements in UK, this is done automatically by using the so-called noise and track keeping. So essentially there are some ground measuring stations which are not monitored, so the data are captured automatically and extracted remotely from some office at some of course parts of the airport, and sometimes are supplemented by handheld measurements. In these cases, you can find sometimes that the measurements are basically streamed live on some web tracking systems. For example, if you go on the web, you can find that for Heathrow Airport and perhaps some others around the world, they will show you what is the noise, basically noise level on a live system on the web, so you can tell which airplane is flying at which moment and what is the noise measured at each of these community noise microphones. Microphones will look like this. What you see on the left of the page is an attended monitor. So this microphones tend to be several meters high. It can be 4 meters high or 6 meters high. Sometimes they're placed on top of buildings. And on the right, you see what is called attended monitor. This is a microphone which we use normally for doing our measurements. This is called the SLM, which is sound level meter. It's not placed like this. It's normally placed horizontally 1.2 meters from the ground. This is the what the regulations require. So the standard practice is to have a 1.2 meters above the ground in order to do airport measurements. They're oriented horizontally for grazing incidents to avoid effects of directivity. and it's calibrated that 1 kilohertz sound using two sort of noise levels, one at 94 dB and another one 114 dBs. When you do this, you need to note the atmospheric conditions, the GPS location where you're placed. The atmospheric conditions means, of course, wind direction, temperature, and relative humidity. This is important because the noise propagation does depend very much on that. Clearly, take note of contamination events. If there is a train, if there is a car, if there is anything around there, just to make sure that there is no contaminating your event. There is a lot of technical reference on this, which is given here. If anybody is interested, just get back to me. I would be happy to give further information. So if you go near the airport and take measurements on the landing side, you see you get measurements like this. This is very good because essentially what it shows is that the peak noise is more or less the same, different airplanes. This is the Boeing 737-800. So you see the peak noise is not very variable. And time zero is when the noise is at its peak and the airplane is roughly 90 degrees just above your head. Okay, so the airplane in this case is traveling from essentially left to right to the page. So you got the time is measured in seconds to the peak and from the peak. So you see that 20 seconds before reaching the peak, and 20 seconds before reaching the peak is several kilometers away. Okay, because of the speed, and therefore you can see that there is quite these are random events. It's very difficult to justify these events by using simple science, because clearly the atmosphere is not homogeneous. There would be gusts, there would be winds, there would be changes of the wind direction, there would be turbulence, and therefore that justifies why the farther the airplane it is, the more difficult it is to have a coherent sound. This particular event here, we associate to a notch change in flap setting. So the airplane is about to land and all of a sudden makes a sharp increase in the flap setting. That happens only in one case, and that releases essentially a vortex which is very noisy and travels backwards, and therefore it can be picked up by the noise device. So you see, it happens only in one case. It doesn't happen in other cases. Also, the good news is that for 10 seconds, about 10 seconds from the peak, the noise is actually quite coherent, and therefore this is actually a good measurement. If you go on the takeoff side, it's much more difficult, because on the takeoff side you have that the airplanes do all sorts of trajectories. They can take off sharply. They can change direction. So it's much more difficult because peak noise is variable. There is a rise and fall, which is variable. The noise level is dependent on the weight, on the climb angle, on the track dispersion, which is obviously quite large track dispersion. And here I'm showing some predicted noise for one generic case, and you see that you are within the bounds of the measurements, but still that isn't good enough. You think that you haven't got the right trajectory to compare with. So that's where the difficulty is. You need to have the right trajectory in order to start making real comparisons with the simulations. So let's go on to part two, which is trajectory management. There is a lot of research on trajectory management. I'll just give you a few examples. So the problem is this: you need to design a safe flight trajectory. Safe means you can do all the optimization you like, but essentially you need to comply with all the flight safety for the airplane, for the airport, and for international regulations. To minimize noise, subject to minimum exhaust emissions, and subject to being on time. You cannot just minimize noise and then go around and add 2 or 3 minutes to your flight, because adding 2 minutes to your flights, it adds time, it adds cost, and ultimately it adds to operational difficulties. So you cannot just minimize cost, but you have a lot of other things to do considering. So if you basically go into preparing an optimization problem mathematically, you find two competing goals, and these competing goals will lead you to a Pareto front on which you need to make a choice whether to do, choose an operational point which will give you minimum noise or minimum exhaust emission, and so on. So I'll just give you an example of some trajectories, etc. Other aspects you need to consider is aircraft control issues, air traffic control issues, and of course the capacity of the airport. I mentioned before the balanced approach. Of course, improvements in land use. This is quite interesting because there are very few airports around the world. I think there are about 6 as far as I know, airports around the world which have been built on artificial islands. There are 4 in Japan, as far as I know. One is Kansai, one is Kobe, one is Nagoya Centrair. And one of the main airports in Tokyo, Haneda, in fact, is also on an island. It's not an artificial island, but the island has been expanded. So it's been, part of it is artificial, so we can call it almost artificial island. And a few others around the world. I know there is, for example, one in Turkey, and the one is Macau. Macau is also an artificial island. So this is the interesting thing. So this is Kansai Airport. You can see there is a scale, and clearly you haven't got an issue with the noise in here, because you got several kilometers from let's call it the mainland here, the coast of the city and the airport, which is over here. And the only way you can get there is by train, okay? And the landing and takeoff direction essentially is parallel to the coastline, and therefore the issues of noise are basically zero. It's something you probably don't need to worry about. But clearly, you know, as I said, there are only 6 airports around the world, as far as I know, could be perhaps one more, where you don't have to worry about noise. Clearly, you cannot do this in most of the world, where you have thousands and thousands of airports. If you were to basically design a new airport position, so look at the graph here on the right. What you have is essentially you have to look at where the annual winds are. So we've got 80% annual wind coming from the west. So you got a city, this would be typically London. And therefore the ideal airport for a city like London would be on an island, you know, to the east, or an island to the south, because the winds come from here. Unfortunately, what happens is that we have a very busy airport to the west, which is London Heathrow, and this is just where the airport shouldn't be. But, you know, that's where we are, and we can't move the airport, and we can't move the city. So this is the situation as it is. So we can't afford doing like we do in Japan, and just to build airports on artificial islands. But just a bit food for thought, you know, if you want to think, you know, where to put an airport or where not to put a new airport. So let's look at the role of aircraft management. So you got noise airfield, particularly ground noise, which is actually quite annoying. You got taxiing in and out of the gate. You got dispatch procedures. For example, the airplane sometimes has to taxi for several minutes. And to reduce noise, you want to minimize the time to the gate. So once you have landed, you want to get to the gate as quick as possible, also to save fuel. And in my opinion, you know, large airplanes have dispatch priority. Now, it might sound, you know, obvious, but in many cases it is not, because when you look at taxi times at very big airports, you know, large airplanes have very, very large taxi times. There is a lot of work on airborne considerations. Of course, there is technical literature. I need to just move on to this, but if anybody's interested, just get back to me with the questions. Trajectory optimizations, you can do all sorts of things these days. You can do arrivals, you can do takeoff, you can look at lateral noise. And there are a number of procedures which have been tried. Some of them have been actually applied at very many airports around the world. For example, continuous descent is one procedure. Steep descent is also another procedure where the glide slope is greater than 3 degrees. 3 degrees is the normal for commercial airplanes. Some airports like London City, airplanes are required to demonstrate a glide slope of 5 or 5.5 degrees in order to be allowed to operate from that airport. And finally, there is a displaced threshold when airplanes on landing are allowed to land, farther away from the runway threshold in order to decrease noise on communities on the landing side. So you can basically sometimes do a runway alteration depending on the winds. For example, as I said in a previous case, if you have 85% westerly winds and 15% easterly winds, you can alternate the direction of takeoff and landing. This, of course, is not something that can be done on the minute. It has to be planned in advance, maybe several hours in advance, in order to allow pilots to replan their arrival and departure trajectories. And there are, of course, the runway directional preferences, as I said, either westbound or eastbound, northbound, southbound, and so on. Departure operations are actually quite a few. They're called, some of them are called an NADP, which is departure noise abatement departure procedure 1, procedure 2, then it would be an ICAO procedure 8, procedure B, and other procedures. That some of them are being codified. For example, the Federal Aviation Administration has these abandonment procedures codified in a technical document, which is listed here. So just to push forward on this point here, so just to show you what is the case of noise abatement. So what you have is a brake release point in here, and then you have a takeoff. The takeoff distance, by the way, depends on the airplane, depends on the weight. So the takeoff can be here, can be there. So essentially, this is just a generic situation. So takeoff at point A, then you be using takeoff thrust for up to the point B, where you reach an altitude, say 800 feet, and you reach a speed, which is the takeoff speed plus 20 knots. At that altitude, there is a cutback in thrust. So essentially, the airplane maintains speed, but with a lower thrust until it reaches point C. Point C is 3,000 feet. At that point, there would be so-called climb thrust. And what they need to do is just to guarantee there is a minimum climb rate, which, as far as I know, is 4 degrees. Now, if you have been flying, perhaps not recently, but before the pandemic, you ever felt a bit of unease the moment that you seem to be climbing very fast, and all of a sudden the airplane seems to be stuttering, reaching a certain altitude. And if you had the feeling, it's because you are at the situation here where at 3,000 feet, the pilot has decided to cut down on the thrust. And the reason why it does this is that because if you have a community on the ground, here you have houses, and you have people on the ground, you got schools, etc. You want to reduce noise, and the way to reduce noise is to use thrust and pass the terra. Then you increase again, and you keep climbing again. So this is one of those procedures, and it's called the NADP1, or noise abatement procedure 1. There are other ones, but just to get an idea of things can be done on the operational side. So in elements of optimization, there is a lot of science in here. Again, I haven't got the time for doing this, but I mean the search space for this optimization is non-convex, because you got the noise metrics which are integrals in some form or another. They're not differentiable, and therefore when you have gradient methods, the gradient methods often they do not work very well. So we need to use non-gradient methods. And sometimes you use, responsive phases sensitivity analysis to just see what, by changing certain parameters, what happens to the trajectory, and of course to the noise. Okay, so I have to leave this behind, and again, anyone who's interested, just get back to me on this aspect. So this is an example of trajectory. Case study in Manchester Airport. So we have is an airplane, is a 737. So this is the airport here on the top right of the graph. And the airplane essentially does what we call a Samba 1Y routine. And now this Samba is nothing to do with singing and dancing. So the airplane is not singing and dancing, but effectively what is required to do essentially is avoid communities which are to the south of the airport. So this community here is called Knutsford. And therefore, essentially the airplane, as it's taking off, essentially passes to the north of the town, and then it does a southbound turn away from it. So by keeping the distance, of course, that way. So it's a way of reducing noise. Now, we've been going there to take measurements in the past at the point called M. So a few years ago, I even sent a student to take measurements in there, and we got some.
This is the Manchester Airport.
Data for this. So this is actually quite a public park, and to take measurements we have to ask permission from the park rangers. And this is another interesting thing, that you go and try to take measurements of airport noise, and you need to seek permission. And the moment you go and seek permission, they ask you, what are these for? And we've been asked so many questions so many times that sometimes you think, we don't really want to do this. It's because we don't want to be viewed as proxies of possible complaints between the park authorities and the airport authorities. And they said, we just want to do a scientific work in here. So anyway, this is a trajectory for what's called the Samba 1Y routine, southbound, and therefore the airplane had basically changed routes in there. So in doing some trajectory optimization, we've done this, for example, with the three different types of aircraft, which are three essentially weight classes. One is the Embraer 195, which is a commuter airplane, so is a turbofan airplane used for relatively short flights. So light, well, it's not really light aircraft. I mean, is a commuter airplane. Then you got the A380, which is the big beast, and then the A320, which is the backbone of aviation. So all of these airplanes are doing a samba route, but as you can see, there is quite a different trajectory, because, for example, the 195 is being light makes less noise, and therefore is required to maintain, it can be required to maintain a shorter distance from this point. So we have a reference point here in this town called Knutsford. The case of the A320 is in a way is a mid-weight sort of airplane, is more agile. In that case, it can do turns relatively easy. So you see that the radius of curvature is actually quite large there. The case of the Airbus A380, this is a big beast, and the turning around with one of those is slightly more complicated. So you see three trajectories which are completely different. So this is optimization, which is done in two different ways. So when you look at the solid lines, you have essentially minimum noise. A minimum noise at the point in the town of Knutsford means a minimum EPNL value. However, we also done a multidisciplinary optimization in which we actually consider the total minimum cost. And the total minimum cost is a minimum noise plus minimum environmental emissions plus minimum time, if possible, subject to complying to safety regulations. Now, the trajectories are slightly different, as you can see from the dashed lines. These are only, I would say, this is only what we call the tracks of the flights. The altitude is actually quite different, and perhaps I should have shown also the altitude, the distribution of the flights, which is different from each airplane. But you just get an idea of what kind of operations you need to do depending on the airplane. Again, this is for minimum fuel consumption. So minimum fuel consumption, not taking into account at all the noise, means that you're doing a much sharper sort of straightforward trajectory, and of course you get closer to the town of Knutsford because noise is not a constraint in this particular instance. Now we can, just as one final example, I want to show you that we can model very detailed airports. This is a model of London Heathrow. And so what you can see in this graph here is this first layer, which is the airplane model. Now the colors are not the colors in reality. Each color denotes one acoustic property on the ground. Okay, so what we call acoustic impedance. And now I've been clever enough to actually call each acoustic impedance value with the same color as it happens in nature. So this is like a map, but the reality is I'm not showing green and blue like water and grass. This is just an impedance map. And on top, what you have is the noise departure, noise footprint. Now, because this calculation requires a lot of time to run, I think this one was particularly 6 days. What I've done, I have basically implemented another algorithm which basically removes, blanks out the areas of water. So where there is a water, I just say if there is a wide water body, do not bother calculating the noise in there, on the basis that the fish don't care about the noise. And that saves a bit of time. So my 6 days computation are also based on the fact that all these water bodies have been blanked. And ultimately what you get is this detailed EPNL noise map. And this is what I was mentioning before. And you will find lots of these maps around airports, but they are made for, of course, hundreds of operations every day. This is done for a single aircraft. Of course, this is doing a bit of research on this. We won't be able to expand equally on a full scale, but I'm going to show you in a moment what that means. So the other thing I want to do essentially take the trajectories we simulate, and we use Google Maps in order to synchronize them with the airport. So just to make sure that our trajectories are essentially flying in the right position. And here, in fact, there is another example I want to show, that there are some microphones. This is one of the official microphones of the airport. It was not in the place we thought when we went to look at it. So the original position was actually there, but in fact it wasn't there, and the microphone was over here. So there is an official microphone for community noise, and what you can see is that it is close to a railway. So what you see here is a railway, and this is the railway going to the let me change color in here. So this is the railway going to the airport, and here is a road which often is busy. And what you have is a microphone in here. So you see there is an issue of contamination. Here is one of the large car parks of the airport. So one thing I mentioned earlier was that you can have displaced landings. Displaced landings are possible at airports which have very, very large, very long runways of the order of 4,000 meters. One example of this is Frankfurt. So what you essentially have, instead of landing, the conventional trajectory is a trajectory 1. Okay, so basically you land, so this gamma here is 3 degrees. So you land at this point here, which is called x equal to 0. So the displaced landing is this moving the airplane to land over there. So if you have a people over here, so clearly the minimum distance between the airplane and the receiver before was like this, and now becomes like that. So by increasing the distance between the receiver and the airplane, so you expect you reduce noise. And the other thing you do, you have this steep descent, which is this trajectory named 3, which is steeper approach, can be 4 degrees, can be 5 degrees, but this is only possible for relatively small airplanes. So the Airbus A380 wouldn't be able to land with that sort of trajectory there. So the last thing I want to do before concluding is that I didn't talk about the simulations very much. That would take me too long. But essentially what we need to do is this. We need to recognize that the problem of aircraft noise simulation is very complicated, and therefore we need to take an overall approach which takes into account the fact that the more you want to simulate, the more you need to leave behind. Okay. So what we do is we do a component analysis. So we look at the noise of each noise component. Then we want to do aircraft noise. We look at noise events, and eventually the noise footprints, as I said, in the case of London Heathrow. To do some noise contours for multiple airplanes. At the moment, we're not able to do that because of extreme computational complexity. Now, what happens also is that if you want to do component analysis, you can actually use physics-based methods. If you want to do the aircraft noise, you maybe need to go toward the semi-empirical methods. And then you basically building complexity level, essentially the accuracy decreases. And you get to a point where if you want to do noise contours for the entire airport, for hundreds of aircraft movements, essentially you rely on an experimental database. Here I call the big data process, but is not done like this because what is used is an approach called NPD, which is noise, power, distance. So it's another area which is used by I would say the industry, but essentially would be the airports. So we don't really do this. So using databases in order to do this map. So we don't do this, but this is the way to just sort of approach these problems of extreme complexity. And if you want to retain the physics, of course, the only way you retain the physics is you remain at the component level. So you simulate the flap, or you simulate the fan of the engine, and so on. So this is just to give you just a snapshot of the complexity of the entire problem. And this is my summary. So aircraft noise is a major environmental concern. Regulations have been established now for quite a few years, getting more and more strict. But I have to say that there are no regulations in place for supersonic flight because, of course, there is no supersonic airplane flying, at least no commercial supersonic flying at the moment, maybe in the future. There are several aspects of psychoacoustics, sorry for misspelling here, psychoacoustics and engineering, and need to be considered. So engineering is one thing, but you need to consider how people actually react and to annoyance and so on. There's very scant comparison between noise contours. Possibly there are legal implications because if you take two different models, it will give you different noise contours. And the robustness and reliability of the scientific methods are not been fully proved. So this concludes my talk, and thank you for listening to me. Any questions, just please.
Sorry, that is the presentation by Prof. Filipponi. So what do you think about it? Did you understand about the aircraft noise? So you are lost somewhere. Okay. Did you follow the presentation?
Yes, Doctor.
Yes,
I'm
Doctor.
actually quite amazed that even the flight path for one aircraft, it is different from another one model to another.
Yeah.
So there are so many considerations to be taken when actually considering which path one aircraft will take. I always thought that it is the same for all the aircrafts, Doctor.
No.
But after this presentation, now I know that it's different for each model.
Yeah. And that is also important, especially not only during takeoff, but as well as but the same consideration also being taken for the highway on the sky, because we have hundred of aircraft, right? 100 of aircraft, or even 1,000 of aircraft, I'm not sure, flying above us now. So there are different trajectory, of course, different altitude being given to specific aircraft, so that it is safe. That's one, as well as to allow the control tower to monitor the aircraft, each of the aircraft easily. Those aircraft within their territory. Okay, so this is very important for all aircraft, not only for airlines but also for small aircraft. If you want, let's say, to fly from KL to JB, for example, using a small aircraft, to Ipoh, for example, right? Or you want to fly a helicopter to observe what's going on in Shah Alam, for example, right now, or in Hulu Langat, right? To get a better overview of what is going on down there. So all those are being considered, not only for fixed wing aircraft, but also for other types of aircraft. Okay, so for this one, we are talking about noise. So later on, if let's say you involve with any consultant, for example, okay, I don't know, probably the next 10 years or the next 15 years, you become somebody and you are involving in a project of developing a new areas with an airport. So yeah, you need to also consider all those items as what we have seen just now. Okay, so you need to allow a certain distance between the airport and which is away from those dense populated areas. One is because of the noise, as well as for the safety. If let's say the aircraft have some mishap or any problems, mechanical problems, so there are area where the aircraft can glide and perform emergency landing, okay, if needed. So that is the things. But the topic that we have discussed during the lecture is about the structural limitation of the aircraft, which is the VN diagram, right? So I think that's pretty much of the lecture for today. Okay, I have another meeting actually. I have to attend the faculty meeting at the same time here. It is on my phone right now. Okay, thank you very much for your time. I hope you can continue working on that particular problems, which is not yet 100% complete, okay? And you can re-upload it into the Putra Blast when the Putra Blast system is okay. Because this morning I got a message, I got an email from the UPM IT department saying that they are doing some work on it. Okay, so thank you. Stay safe. Okay, we meet again next week on Monday. Assalamualaikum warahmatullahi wabarakatuh. Okay, bye.
Waalaikumsalam. Thank you, Doctor.
Have a nice day, doctor.
Thank you, Doctor.